Hey, so far we have mostly concerned ourselves with series that have only positive terms. Today we're going to look at a special type of series that can have positive and negative terms, known as alternating series. And it will probably come as no surprise to learn that an alternating series is defined as a series that has terms that are alternately positive and negative. And here are some examples. The first one, the alternating harmonic series. The usual harmonic series is 1 plus a half plus a third plus a fourth, etc. Same thing, it's just that we've now made every other term negative. In summation notation, we managed to do that by taking -1 to some power, usually either n or n plus 1, or maybe n minus 1, depending on whether you want the first term to be positive or negative. Another fine alternating series, -1 plus 1 minus 1 plus 1 minus 1, etc., which is just the sum n equals 1 to infinity of -1 to the n. And one more, -1/2 plus 2/3 minus 3/4 plus 4/5, and on and on and on forever. And here we have it in its summation notation, another alternating series. And the natural question when presented with an alternating series is, how do you decide if an alternating series converges? And it turns out to be rather straightforward. Here we have the alternating series test. Suppose you have an alternating series, some -1 to the n of a sub n, where each a sub n is some positive number, so it's actually legitimately alternating. Well, that alternating series converges precisely if two things happen. If each term a sub n plus 1 is less than or equal to the term before it, meaning the terms are decreasing. And the second thing you need is that the limit as n goes to infinity of the terms is equal to 0. And so that's it. If the terms are decreasing and going to 0, then the alternating series converges. Before we move on, we should probably note that you can't use the alternating series test to say that an alternating series diverges. It doesn't say that if this doesn't happen, then an alternating series diverges. If you had an alternating series and you wanted to show that it diverged, you might be able to use the divergence test, show that the terms don't go to 0, and that would be enough to show that it diverges. And it's also worth noting that the for all n is, as always, not necessarily so strict. It just has to be for all n greater than some number. You can throw away the first finitely many terms and still get away with the same test. So if the terms were decreasing, starting with the 100th term, and the limit of the terms is equal to 0, that would be good enough to say that the series converges. And in a moment, we'll look at a brief proof of the alternating series test. But first, let's give it a try. Look at the alternating harmonic series, 1 minus a half plus a third plus a fourth minus a fifth, and on and on and on forever. Well, the terms are decreasing. A third is less than a half, a fourth is less than a third, a fifth is less than a fourth, etc. That goes on forever. And the terms are certainly going to 0. As n goes to infinity, 1 over n goes to 0. And that's enough to tell us that the alternating harmonic series converges by the alternating series test. So a pretty powerful test. Let's look at a proof of the alternating series test. And not to worry, it looks worse than it is. Let's start out by considering the even partial sums. So S2, which is A1 minus A2, and S4, which is A1 minus A2 plus A3 minus A4, S6, A1 minus A2 plus A3 minus A4 plus A5 minus A6, etc. And you can see I've grouped the terms together, two at a time like this. And that's for a reason. It's because since these terms are decreasing, we know that each of these grouped pairs is a positive number, or at least a non-negative number. A2 is less than or equal to A1, and so A1 minus A2 has to be non-negative. And that's what the part of the proof right here says. It says that each of those pairs is non-negative because the sequence is decreasing. And here we have an expression for the arbitrary even partial sum. So it goes from A1 minus A2 all the way up to some even number or some odd number minus the last term a sub 2n. And the key observation is that each one of these grouped pairs is non-negative, and so the sequence of nth partial sums is increasing. We're taking some number, adding some non-negative number to it, and then another one, and so each even nth partial sum is at least as big as the one before it. So that's this statement here, that the sequence of even partial sums is increasing. We can also rewrite this expression for the arbitrary even partial sum like this. In other words, a sub 1 minus a sub 2 minus a sub 3. Well, if you distributed there, you'd get a sub 1 minus a sub 2 plus a sub 3, and you'd get exactly the same expression that you have here, except that I've carefully regrouped the terms. And the reason is that just like before, each one of these pairs, and all the way down to and including this, is a non-negative number. And so we're taking some positive number here, a sub 1, and subtracting positive or at least non-negative quantities from it one after another. And that's what lets us conclude that the 2nth partial sum has to be less than or equal to that first term, a sub 1. We took a sub 1 and just subtracted quantities from it. And so the biggest it could possibly be is a sub 1. And here's where I cheat a little bit. I say, well, the sequence of even partial sums is increasing, and it's bounded above by a sub 1. In other words, it's increasing, but it can't get larger than a sub 1, and that means it has to converge. And why I'm saying that I'm cheating is, well, that's a powerful theorem known as the monotone convergence theorem, and probably I should have introduced it to you first, but at least it makes some sense intuitively. If a sequence is increasing but can't get beyond some point, how could it possibly diverge to infinity? It has to stay less than that point, and so it is converging to something. And I'm going to call that something L. That's what we're doing here, saying that if we've just determined that the sequence of even partial sums converges, then it converges to some real number, and we'll call that real number L. Okay, moving right along. Having already determined that the sequence of even partial sums converges, we have to look at the sequence of odd partial sums. Well, what is an odd partial sum? Well, the odd partial sum s sub 2n plus 1 is just s sub 2n plus one more term, the 2n plus 1th term. And taking limits on this equation right here that we just looked at, we get this set of limits right here, that the limit as n goes to infinity of s sub 2n plus 1 is just the limit of each of the components that make it up. The limit as n goes to infinity of s sub 2n plus the limit as n goes to infinity of a sub 2n plus 1. And the beauty is we know both those limits. The limit of the even partial sums is L, and the limit as n goes to infinity of the terms is 0. That's the second condition in the alternating series test, that the terms are going to 0. And so the odd partial sums also converging to L. And that's pretty much the punchline. Once you get that the even partial sums and the odd partial sums both converge to the same value L, now you can say that the sequence of partial sums converges to L. And that's the same thing as saying that the series converges. And if you didn't like that, fine. I do suspect that you could follow every single step of that if you just focused on it a little bit. But really, I'm just trying to show you why the alternating series test works. From a practical point of view, you need to be able to apply the alternating series test. And so all you're going to do is, given an alternating series, test whether or not the terms are decreasing, and test whether or not the limit of the terms is equal to 0. If that's true, then you can say that the alternating series converges by the alternating series test. Let's look at an example. Here we have an alternating series, the sum n equals 1 to infinity of negative 1 to the n plus 1 times n plus 2 over n times n plus 1. We want to know, are the terms decreasing, and is the limit of the terms equal to 0? The limit is probably the easier part. It helps if you expand the denominator or distribute in the denominator. And then you could proceed from this point either by dividing numerator and denominator by n squared and applying the limit laws, or since this is of the form infinity over infinity, we could use L'Hopital's rule. And applying L'Hopital's rule, we would get that this is the limit as n goes to infinity of 1 over 2n plus 1. That's the limit of the derivative of the numerator divided by the derivative of the denominator. And that limit is clearly equal to 0, so we've satisfied one of the conditions of the alternating series test. The terms are going to 0. Often the harder condition to satisfy is to determine, are the terms decreasing? We need to show that a sub n plus 1 is less than or equal to a sub n. And dividing both sides by a sub n, it's often easiest to show this by trying to prove that a sub n plus 1 divided by a sub n is less than or equal to 1. And what is a sub n plus 1? Well, it's the n plus 1th term, and just like if you were trying to find a sub 5, you'd plug in a 5 everywhere you saw an n in the general formula for the terms. If you want to find a sub n plus 1, you plug an n plus 1 in for n everywhere you see an n in the general formula for the terms. In other words, a sub n plus 1 is n plus 1 plus 2 divided by n plus 1 times n plus 1 plus 1. And this is divided by a sub n, which is just n plus 2 over n times n plus 1. Lots of simplifying to do here. What have I done? Well, in the numerator, I took n plus 1 plus 2 and wrote that as n plus 3. And then I took the n plus 1 plus 1 and wrote that as n plus 2. And then I said dividing by n plus 2 over n times n plus 1 is the same thing as multiplying by n times n plus 1 all over n plus 2. And there's a little simplifying we can do before we get down to the hard work. In particular, there's a factor of n plus 1 in the numerator and in the denominator, and so those cancel. And so we get that a sub n plus 1 divided by a sub n is this expression n plus 3 all times n all over n plus 2 times n plus 2. And our goal is to try to show that that is less than or equal to 1. If we can do that, then that will tell us that the terms are decreasing. And if you distribute, you get in the numerator n squared plus 3n, and in the denominator n squared plus 4n plus 4. And if I rewrite the 4n in the denominator as 3n plus n, then in the numerator I have n squared plus 3n, and in the denominator I have n squared plus 3n plus some other positive stuff. And so this is clearly less than 1. And that's what I was trying to show. That tells us that the terms are decreasing just like we were hoping they would be. And having shown that the terms are decreasing and going to 0, we can now claim that the series that we're looking at converges by the alternating series test. Just for the record, there's another way to show that the terms are decreasing. If you didn't like what we just did over there, you could consider the function f of x equals x plus 2 divided by x times x plus 1, which is just x plus 2 over x squared plus x. And we know how to tell when a function is decreasing. It's decreasing where the derivative is negative. To find the derivative of this function, you need the quotient rule, ho d high minus high d ho over ho ho, or however you learned it. And after you do a little simplifying, you get this expression right here. And you can see, first of all, the denominator is squared, so it is always positive. And for all real numbers n greater than or equal to 1, the numerator is negative. Every term in the numerator is negative for positive numbers x. And so this function decreasing certainly from 1 to infinity. And that would be another argument that the terms of the series are decreasing, and we could make the same conclusion. Therefore, the series converges by the alternating series test. Let's make an observation. The harmonic series, sum 1 over n, diverges. We've seen that a number of different ways. but the alternating harmonic series converges by the alternating series test. On the other hand, the p-series, sum 1 over n squared, converges, and it's not hard to see that the alternating p-series, sum negative 1 to the n times 1 over n squared, also converges by the alternating series test. The terms are very clearly decreasing and going to 0. And so it would be nice to have some sort of terminology, some sort of way to make a distinction between alternating series that converge only because they're alternating and alternating series that would converge whether or not they were alternating. And no surprise, we do have such terminology. We say that a series converges conditionally. If the series converges, but the sum of the absolute value of the terms diverges, meaning if you turned all the terms positive, the series would diverge. On the other hand, a series converges absolutely if the series converges and the sum of the absolute value of the terms of the series also converges, meaning turn all the terms positive and it still converges. For example, the alternating harmonic series converges conditionally. It converges, but if you looked at the absolute value of the terms, if you looked at the series of the absolute value of the terms, that would be the harmonic series, which we know diverges. On the other hand, the alternating series, sum negative 1 to the n times 1 over n squared, converges absolutely. It converges by the alternating series test, but if you looked at the sum of the absolute value of terms, that would be the p-series with p equals 2, sum 1 over n squared, which also converges. So that series converges absolutely. For what it's worth, sort of the standard question about an alternating series is, does it converge or diverge? And if it converges, does it converge conditionally or does it converge absolutely? So you'll need to memorize what those definitions are. And after you've tested an alternating series and determined that it converges, say, by the alternating series test, you'll then have to look at the series of the just positive terms, the corresponding series that only has positive terms, and make a determination, does that series converge, before you can decide, does it converge conditionally or absolutely. And one theorem that can help you somewhat in that effort is this one right here. This says that if a series converges absolutely, then it converges. And in a minute we'll look at a quick proof, but first let's show why this is so useful. We already know that the p-series, sum n equals 1 to infinity of 1 over n squared, converges. And so by this theorem, the alternating p-series, sum negative 1 to the n, 1 over n squared, also converges, because this series above right here, well, these terms are the absolute value of these terms right there. Which is to say there's no need to apply the alternating series test once you've shown that the series of positive terms converges. If the series of positive terms converges, then the alternating series automatically converges by this theorem. All right, let's look at a quick proof of this theorem. So suppose we have some series and we know that the sum of the absolute value of the terms converges. This observation right here is true for any number. Imagine a sub n is negative 7. Well, negative 7 is certainly less than or equal to the absolute value of negative 7, which is positive 7, and it's certainly greater than or equal to the negative absolute value of negative 7, which is negative 7. And so that would say negative 7 less than or equal to negative 7 less than or equal to 7. In fact, this term in the middle here is always equal to either this term or that term. And so I'll let you convince yourself that that's true. It certainly is. And then if you add absolute value of a sub n to all three sides of that inequality, you get this expression right here. The next line, since we're assuming that some a sub n, some absolute value of a sub n converges, that certainly means that the sum of twice the absolute value of a sub n converges. You could pull the two outside of the series. And we've got that the terms of this series are smaller than the terms of that series. And so that tells us that this series converges by the comparison test. And then here comes the punchline. The sum a sub n is this convergent series minus this convergent series. So this is just some number and this is just some number. And that means that this must converge to some number as well. And that completes the proof of the theorem. And before we call it a day, I'd like to show you one more interesting example where you can use this theorem above. Look at the sum n equals 1 to infinity of the cosine of n over n squared. Now the cosine of n can be positive or negative, but it certainly doesn't alternate. So this is not an alternating series, it's just a series where some of the terms are positive and some of the terms are negative. But what we can say about the cosine of n is that it's always between -1 and 1. That's a property of the cosine. So the absolute value of cosine of n over n squared is always less than or equal to 1 over n squared. And since we know that the sum 1 over n squared converges, this tells us that the sum of the absolute value of the cosine of n over n squared converges by the comparison test. And that's enough to tell us that the sum n equals 1 to infinity of the cosine of n over n squared converges by the theorem above. Since the series converges absolutely, it converges. Okay, I'm well aware that that was a lot of material to learn, but the alternating series test is the main part, and it's very simple to apply. So keep that in mind. And then there's just two very simple definitions, the definition of conditional convergence and absolute convergence. So I totally understand that it will take some practice. Luckily, I'm giving you some practice. There's a homework on this stuff. Work hard on it. Have some fun with it. Bring questions to class. Looking forward to seeing you there.